So, Maggie, over to you.
Okay, good morning. I'm going to talk about a methodology that we use in RPS for screening to identify EOR projects, and I'll also talk a little bit about the proposed developments for that screening methodology. I'll try to. Do I have to turn it on?
You've done something.
Oh, right.
Oh, you must have done it. So the Maestro methodology provides an efficient framework for the selection and ranking of candidate fields for a range of enhanced ore recovery processes. It's a combination of analytical and numerical software tools which are embedded within a systematic procedure that enables the most efficient use of resources and also ensures consistency of results across different fields and EOR processes. So that methodology is then applied by an EOR expert, and using field knowledge data from the operators, so using the reservoir engineers' expertise knowledge of the field. So I'll just give a little bit of the history of the development of Maestro. The EOR screening was originally developed by Subsurface Group at Winfrith in Dorset, that some people may be familiar with. It was originally the Subsurface Group of AEA Technology. And that group is now the Specialist Reservoir Engineering Group of RPS. So during the 1970s and 1980s, there was extensive research carried out on EOR processes for the UK government, and that involved both experimental work within the laboratories there and theoretical work. In 1989, a decision was taken to develop an EOR screening code, and that was a joint initiative between what was the Department of Trade and Industry at that time and the Norwegian Petroleum Directorate. And then for the next 3 years, a project was undertaken to screen all the UKCS fields for EOR potential. And that was successfully completed in 1992. And just as a matter of interest, we went back about 10 years later and we looked at the number of EOR projects that had actually happened in the North Sea and the UKCS, which were mainly gas injection projects at that time. And we found we'd had a 100% success rate in actually predicting those in the original EOR screening. You'd probably be quite interested to go back again now and do the same exercise. Then in 1996, we developed a commercial version of the EOR screening code, which was called Maestro. And that then enabled us to carry out EOR screening worldwide for different clients. And that software has been used almost continuously since then on different EOR projects around the world and for different oil companies. In 2000, between 2000 and 2002, we undertook a major redevelopment of Maestro, and this was largely to take advantage of the progressions in computer power. And at that time we split it into two modules: performance indicators, which was an analytical screening, and rapid simulation, which is based on simulation of simple models. And that brings us up to the current day, when we're again now looking at Maestro and how we might update the methodology in light of new advances in EOR. And as part of this, we're working together with the BP Institute in Cambridge that are doing some research into some methods for us. So it's very difficult to define what a typical project using Maestro is, because it's a very flexible tool. So it can vary between screening a whole country's portfolio of fields to just looking at the EOR potential in a single field for a single process. And it's even been used for non-EOR projects, such as a front end for setting up water flood calculations. But as far as generally, the objective is to investigate the potential for enhanced recovery using either gas, chemical or thermal methods, and to rank those in some way. So to rank the performance of different displacement processes and reservoirs. So we're looking at different reservoir and process combinations. And then often we need to then look at an indication of how economically viable those processes will be, and even to start doing first pass optimization studies of the best performing processes prior to then moving on and doing more detailed modelling. So this is a schematic of the methodology we use. So we start off with a field portfolio. Initially, we may do some binary screening, particularly if there's a large number of fields to be looked at. That helps to reduce the number of fields that we're looking at. Then we would go into the analytical screening module, put the data into that, which eliminates more fields, bringing the numbers down to a number that we can do in screening simulations, numerical simulation, and finally detailed appraisal, which would lead on to an EOR project being carried out. So this arrow here just gives some idea of the sort of amount of time each stage would take. So for the binary screening, we can do very quickly for each field, so consequently we can do a large number of reservoirs. And as we go down the arrow, the amount of effort required increases until we're looking at months for detailed appraisal, but when we'd only be looking at probably one project. I'll just say a little bit about binary screening. Binary screening is essentially just looking at a range of parameters, comparing that against the properties of the reservoir and either giving it a pass or a fail. And if it passes, then you rule it in. Those ranges do tend to vary a lot depending what source you look at, and they tend to be derived from where projects have been successful or from laboratory or theoretical experiments. There's a number of drawbacks with that. Now, this is just one example of EOR projects that have been successful, and it's looking at oil gravity and depth. So you can see there are clusters of thermal processes tend to be more applicable at the lower APIs than the chemical ones, and at the lighter oils, gas processes tend to be more applicable. So we can define ranges, but there are a number of pitfalls because although we see we have a cluster here, there's quite a lot of outlying points here. So if we defined our binary screening range as this shape here, we would actually be screening out some of these points very early on in the process, which is something we don't want to do. So you can end up with a situation where the ranges are so large that they really don't rule out very much at all. And the other issue is that although we have gas processes here at this depth and this API, clearly there's a lot of reservoirs within that range which aren't applicable for gas. So we may be ruling in a lot of fields which actually wouldn't be applicable for gas. In terms of developments that we can do on binary screening, it's fairly limited really. We can increase the ranges. So as I was saying here, this here is a picture of temperature. So this could be stability of a polymer, for example. So in existing technologies, polymers tend to work between 50 and 200 degrees Fahrenheit, which would give us our range for screening. But there's now new technologies emerging with new chemicals which are actually stable at much higher temperatures. So we need to expand our range to go up to 300 degrees Fahrenheit. The other thing that we can try and do to improve binary screening is, rather than have an abrupt change from 0 to 1 or fail to pass, we can introduce what we call fuzzy screening. So you actually get a score between 0 and 1 depending on what the parameter is. That can be useful if the number of fields is so large and you're only using binary screening, because it does give you an opportunity to rank them a little bit. Moving on then to the next stage in the methodology, the analytical screening, which uses, this comes into Maestro proper really, and it uses the performance indicator module that was developed around 2000. This works on the basis of a number of performance indicators depending on the data that's submitted. So the key performance indicators tend to be numbers which reflect the ratio of viscous to gravity forces. And there are a number of those that are published. Some of those I've put here. There's Stone's number, Crane's number, Dietz numbers. And then there are other numbers which have come out of some of the research that was done at Winfrith. So those performance indicators are calculated, and then depending on whether the flow is viscous or gravity or where it is in between, there are a number of different analytical techniques which calculate displacement efficiency. So that's the next key parameter that's used, is the displacement efficiency. And displacement efficiency is split into two groups. There's the microscopic displacement efficiency, which depends on the initial saturations and the residual saturations to the various fluids, and uses things like Buckley-Leverett theory and looks at miscibility, the effect of miscibility. And then there's displacement efficiencies which are to do with volumetric sweep. So that incorporates aerial sweep, which is on this schematic here, which depends on the ratio of the mobilities of the fluids, for example, and vertical sweep efficiency, which tends to be dependent on the vertical permeability contrasts. And then sweepable volume, which allows regions of the reservoir to be excluded if maybe it's an isolated block with no wells, or attic region which isn't going to be swept. So in assessing the viability then, the first thing we look at is the stability of the flood. If you have good stability, for example, if you inject gas and you have a stable front, you're going to get good displacement efficiency. If on the other hand it's unstable and we're having fingering, we're going to have poor displacement efficiency. So that's a key parameter that we look at. We then can estimate what the incremental recovery from the process will be, and generally that's compared with a water flood. And to do that, we combine the various displacement efficiencies which have been calculated to come up with an incremental recovery. Obviously, the incremental recovery is going to be more in regions which haven't been swept by a prior water flood. For example, you get regions, exclusion zones at the top of the oil leg here as the water moves upwards. And the incremental recovery is going to be lower where you've already had the water sweeping and you're just down to a residual oil saturation. So we use those performance indicators, and also there are economic indicators which allow you to estimate how much of the injection fluids, the chemicals or the gas that you will need to recover a barrel of oil. And then finally, one of the quite important things is to look at uncertainty. So we have procedures for looking at the sensitivities to the known uncertainty on the data to see how robust the solution is. So if over the range of data that's supplied, we get variations in whether the EOR process will be applicable or not, there's clearly an indicator that you need to go back and monitor the field better and get more data. This just demonstrates the difference between the volumetric sweep efficiency and the microscopic displacement efficiency and how that impacts on what EOR processes you might need to choose. So this is assuming our water flood would have a recovery factor of around 45%, and these dots here are on that contour, 45% contour. So if we were actually in this position here, 45% water flood recovery, very good microscopic displacement efficiency, but poor volumetric sweep efficiency. We need to have an EOR process that's going to move us in this direction. So we're looking at EOR processes that will target bypassed oil or attic oil. So it may be a polymer or a crystal gas injection. If on the other hand, we're actually up here, where we have a very good volumetric efficiency, we need an EOR process that's going to target our residual oil to improve our microscopic displacement efficiency. And that might be a miscible flood or a process that includes some surfactant like an ASP, alkaline surfactant polymer flood. Of course, in reality what happens is we're usually somewhere around here, and that's where the skill comes in analysing the results from the Maestro performance indicators. Moving on then to the screening simulations, and this utilises the rapid simulation module. This module is run from Excel, so it's an Excel workbook. Excel initiates the simulations and the results come back to Excel in a form that can compare a number of processes in a systematic way. So the advantages of the simulation approach rather than the analytical. one of the main advantages is you have the opportunity to include a lot more heterogeneity. It's very difficult to include lateral heterogeneity in analytical methods, although you can get a reasonable handle on vertical heterogeneity. But clearly with a simulation model, you have a lot more flexibility in that account. Also, like horizontal wells and multilaterals are obviously a lot easier to model those new well technologies. But the other key important difference is that the simulation models allows you to generate production profiles and injection profiles for the chemicals or the gas that you're injecting, which then can be used in an economic calculation to get a much better handle on how economic the process would be. You can also run sensitivities at this stage, again, to identify and confirm what the critical data might be in the field. And it is a very good tool for doing first-pass optimization studies, particularly something like a water alternating gas process or a WAG process, when it's very easy at this stage to look at different WAG ratios and slug sizes. So typically when we're doing a screening simulation, we would take, if possible, an operator's full field model and take a small sector from that model, which might be a well pair or a well pattern, but a small number of wells. We then take that sector, including all the heterogeneity within that, and we refine it so that we can model the processes in a lot more detail. I'm just going to now show an example of how the kind of results we'd get from the three different kinds of screening: the binary, the analytical, and the simulation. So this is 3 example vertical permeability profiles. So the one on the left here, we have very high permeability contrast with high permeability streaks at the top of the reservoir. The second one is similar, but the contrast in the permeabilities is a bit less. This one here, we have our higher permeability streaks. We have one at the bottom and we have one around the middle. And then this one is much more uniform permeability. If we consider that permeability distribution in a WAG displacement, so we're injecting a combination of water and gas, it might be hydrocarbon gas or possibly even CO2. When we do binary screening doesn't tend to take any account of heterogeneity, or it's very difficult to include heterogeneity within binary screening. So on the assumption that the fluid properties and the other reservoir properties are the same, the binary screening gives us exactly the same score for all the cases. For case 1, which was the one with the high permeability at the top, and case 3, which is the one with the high permeability lower down. When we come to do the analytical screening, we use a performance indicator which tells us how much segregation there will be between the water and the gas that are injected. For a good process, we need the water and the gas to stay mixed together as long as possible. So analytical screening tells us for field 1 that there will be segregation of the gas and water. And for field 3, it also tells us there will be segregation of the gas and water. Although there are slight differences between the scoring system, because there is some difference in terms of the degree of contrast in the permeabilities. But both in the binary screening and the analytical screening, it is very difficult to actually distinguish anything between the two cases. When we come to do the simulation screening, though, this is when we can start to see real differences in how those two fields will behave. On the left-hand side here, we have the example with the high permeability at the top. This is actually immiscible CO2, WAG displacement. So we are injecting CO2 and water at this point. And this is the gas saturation. It shows us where the CO2 is going to go, and that is where we will get the miscible recovery from. So we see what happens is the gas moves upwards and it runs along this high permeability zone at the top, and it then cones back down to the producer, and we end up really not sweeping very much of the reservoir at all. On the second one here, we see here there's some influence from the high permeability layer at the bottom, and some more influence from the one in the middle here, which helps to keep the gas, the CO2 down in the reservoir. So though we still get override here, we've ended up sweeping a lot more of the reservoir in the process. So this might be a viable process. This one certainly wouldn't be. But we'd need to go as far as the simulation in order to discover that. Oh, I missed the arrows out. So obviously EOR has moved on quite a lot from the time when these codes were originally developed. It is interesting how robust they've been though. It's by setting up a fit-for-purpose model and having an understanding of how the EOR process works, they still work very well. However, there are developments that we can be considering. In chemical flooding, when the code was originally put together, we had surfactants and we had polymers. There's now a wide range of new chemicals which are coming on the market, and as we discussed earlier, a lot of those operate over much wider ranges. So they're operating in more extreme conditions, higher temperatures, lower permeabilities, higher viscosities and salinities. Those are quite easy to accommodate in terms of just extending the ranges of applicability for the chemicals. The process is not actually changing that much. Then there are new polymers and chemicals which actually work in a different way, so they have a new flow mechanism. And I'm thinking of things like bright water, which is thermally sensitive, so you inject it and it gels at the water interface, or low molecular weight polymers, which you can inject into very low permeability fields and are useful where you've got fractured reservoirs. Those sort of processes need a little bit more thought as to how we're going to include those within the analytical and the simulation screening. Then there are new processes. There's ASP, which is now being considered quite often. Again, that's really just a combination of the modules we already have. It's a combination of surfactant and polymers, so fairly easy to incorporate into the existing methodology. Foams, low salinity water flood, a little bit more difficult in thinking again how to incorporate those. And then there's finally the problem with the WAG displacements, the difficulty, because WAG is quite sensitive to heterogeneity, we run into this problem which I discussed just now, that the analytical methods actually find it quite difficult to predict whether WAG will be successful or not. So we're working with the BP Institute to look at some ways of improving WAG, improving the WAG predictions within the analytical methods. And this work has only just started, so it's very much in the early stages, but I just thought I would just show you out of interest some of the experiments that they've started to do. So this is a very simple experiment, a Healy-Shaw cell experiment. It's basically 2 glass plates with glass beads in between, and they change the size of the glass beads to simulate different permeabilities. So you can see in this particular picture here, there's different size glass beads there. And this is a series of simulations that they've done injecting pure water into brine. So they've got injecting a less dense water in, and so the coloured here is the injected less dense water that's going in, and here we have a high permeability streak. On this side here we have screening simulations that we've done with rapid simulation to simulate the same process. So if I just run through this series, we see we're injecting our lighter water here, and we're matching it with the screening. In this one, the water has got to the high permeability streak here and starting to run along in both the experiment and the simulation. Now this one is quite interesting. We start to see little plumes coming up here from the high permeability streak. We don't see those in the simulation. I'm not quite sure what the explanation for those is, whether it's some heterogeneity or just the fact that that gas is able to move upwards there. And this is just continuing now. More gas, more lighter water moving upwards under buoyancy forces. But on average, a fairly good match. I mean, there's obviously a lot of limitations to that modelling they're doing, and probably the main one is that it's only 2D. But the fact that we can model it with the simulations will help with that. So the idea behind those experiments is to try and look at trying to develop some algorithms which will take into account the position of the high permeability layers and other heterogeneity within the analytical methods. So just to summarise the talk then, Maestro is an established methodology which provides an efficient framework for selecting and ranking candidate fields for EOR processes by focusing on the most promising processes at an early stage. This methodology continues to be relevant for today's EOR screening requirements, but there are new chemicals and processes which do require developments to the methodology. And research is ongoing to improve the analytical methods for the WAG processes. Thank you.
Okay. Any questions? Please, yeah. Microphone.
I have 2 simple questions. One, that first graph of yours, if I recall, relates recovery to depth. I wonder if you have one that relates recovery to size of field. What interests me is much more moving from North Sea to Middle East, where you have huge reservoirs that you're dealing with. The other one is, I wonder if you could give us some economics of secondary recoveries.
I think the first one, you're talking about this.
The first one, the very first one, if I remember. Yeah. You had a gravity, don't even beyond.
This one, yeah.
Versus depth. I wonder if you had it versus size of reservoir, volume of reserves.
I don't have one with me, but clearly, I mean, it will be quite easy to construct that. I was really just putting this as a demonstration of how to go about binary screening. So I haven't got.
I'm thinking of that simply because depletion rates would be different, recovery rates would be different when you move from small to big reservoirs.
Yeah.
And so I'm just wondering how predictable it will be.
Size of reservoir, I haven't seen that used as one of the most important binary screening criteria. Clearly, I mean, if you have a very small reservoir, then economics is going to come into it. That it probably wouldn't be economic to do an EOR process.
If you move from multiples of billions barrels per field to multiples of billions barrels per field, that is the sort of thing I have in mind. Quarter of a billion or 1 or 2 billion barrels per reservoir.
I think the size, I mean, in terms of the technical viability, when you're talking about that sort of differences in the sizes, I don't think the size of the reservoir is actually going to make any difference as to whether it's technically viable or not, because you're tending to talk about patterns. So a pattern element in your small field would be the same as a pattern element in your larger field. So there was another question.
Economics? Recovered barrel?
Within Maestro, we tend not to go into a lot of detail in economics. What we do is do economic indicators, so that can give you an idea, so you can tell you how many barrels of chemical or how many cubic feet of gas you would need to recover an incremental barrel. But to do actual economics, it tends to be very region specific, very field specific, very process specific. So what we do is we provide the profiles for input for those kind of more detailed calculations.
In your early slide, you showed the filtering process starting off with 1,000 reservoirs and then filtering down and ending up with 1.
Yeah.
Is that indicative of a kind of suitability for EOR of only about 0.1% of all reservoirs worldwide?
No, not really. I mean, it's just giving an indication of how many fields that you might cope with at that level. So, because it's a ranking process, the fact that you only end up with 1 to look at in detail is probably because that's the best process within that, the best field within that field portfolio, not because it's necessarily the only one.
And do you have an indication of what the percentage would be of fields which would actually be suitable if you put the economic dimension to one side?
I don't know that I do really. I wouldn't like to say.
The final comment I've got is on, I think, the penultimate slide and the one before that, where you mentioned those plumes. I thought I could see evidence of the kind of plumes on the model, actually. The nose was kind of coming down.
There's clearly a cone on the model, but you don't get these. Should we go back to those?
Kind of at the top.
Yeah. So I mean, you certainly get this cone here coming down, but what you don't get on the experiment, you get this, but then you get these sort of vertical plumes that seem to be coming up there, which this is much more smoothed in the model. Obviously, there's absolutely no heterogeneity at all in the model.
I was kind of interpreting that as being those plumes that kind of subsumed within that sort of fuzziness on the top right.
It may well be. Yeah.
Okay. All right, all done? Well, yeah, we need to move on, I think. Sorry. Yeah. Okay, thank you, Maggie. Thanks very much.